Good afternoon, everyone. Who's here? As I mentioned in the email I sent, I'm going to review the quiz questions and then I'll continue with the coverage of the inference 6. Probably just have time to do some more problems with proportions. So it's Friday, so this is our last stream, and just watch all the previous videos, read through the notes, send me some problems so Monday I can answer your questions, if not before. So this problem here, if the chance of catching the flu at a daycare center is 20% out of 400 children, what is the approximate probability that 60 to 70 people catch the flu? (60 or 70 people catching the flu. Indicate the assumptions that you're making and verify that it is appropriate to make the assumptions. So to solve this is just to recognize it. This is information given to you about this is P, the true proportion, okay? So they're telling you the proportion in advance. When you're given P, this is a problem. Okay, so you're given P and then asked about the results of a sample. This is involving the sampling distribution of the sample statistic. Okay, so P is 0.2, and this is an SDS problem, well, as the title says. Okay, so some people answered it different ways, but the way it's answered is using formula number 2 from the formula sheet. Okay, not the first one that has to do with the count variable, but the second one that has to do with the sample proportion. So what do we know? We know that provided n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then I get the result that the count variable is approximately normal with a mean NP and a standard deviation NP 1 minus P square root. All right, and that's what I'm interested in. I'm interested in the sample count. So I made the assumption, okay, so let's just verify that this is true. N times P, N is 400 times P of 0.2, so 0.2 times 400 I'm gonna make this a bit larger. Make the calculations on the side. So that's 400 times 0.2 so 80, right? So that is going to be greater than or equal to 10. Let's check the other side. On this end, n times 1 minus p is even larger, right? So 400 times 0.8 is greater than or equal to 10 as well. You can punch that in and verify that for yourself. It's even larger than 400 times 0.2. Okay. So then, it's true that the sample count is approximately normal with a mean of mu of NP. So let's calculate all that. So X is approximately normal with N times P. So that's 80. And N times 1 minus P, N times P times 1 minus P. And then square root. Which is 8. All right, so N times P. Let me just do that calculation on the side. So that's going to be 400 times 0.2 times 0.8 with a nice root around it. And when you do that, you get 8. So now let's answer the question. The probability that between 60 and 70 catch the flu, so that's going to be using X. This is what we want to solve, where X is approximately normal, so our result is an approximation. That turns X into Z when I standardize. And I get between negative 2.5 and I'm giving you enough time to plug this in. And negative 1.25. So these are below the mean results. So what's the chance of being between 2.5 standard deviations below the mean and 1.25? And that's it. You need to answer that now as though it was a normal problem. Okay, so the main thing is that you remember you derive this in advance so you can use it to standardize, all right? And now some of the problems, and I don't know, you might see people doing examples if you go on other YouTube channels, which I don't recommend because you don't have enough time, and I do give you everything you need. If I don't, let me know what's missing and I'll provide a video. You can just calculate these in advance and use them just like you would in the normal, in the unit on the normal distribution. Okay, so now we just have to make a drawing. And I'm going to go from negative 2.5 to, so you see the importance of unit 2 nor, and negative 1.25 you compute or you derive or obtain those from the table and then subtract the bigger one by the smaller one. So you should have your formula sheet at your side, you should have the tables by your side, and your calculator. So negative 2.5, this one is 0.0062. And then the other one, negative 1.25. Is 1056. So you take the big one minus the small one to get the space in between. And that will be your answer. What do you get? So let me know if you see any problems with what I've done, if I've made a mistake or you don't understand, let me know. But my answer is 9.94%. So there's approximately 10% chance that between 60 and 70 people will catch the flu. All right? So that's the first one. How many of you got that? Too creative. Yeah, that happens. So usually that answer should just fall right out. If you're computing a lot, maybe you did something wrong. So that's all right. I'm going to give you another chance. Some people already emailed me about having another chance. So next week I'll do the same thing, and I'll post until 9 or 10. I'll decide how much time to give you. But I'm very happy you guys are trying, and I saw some concerted efforts. Just keep trying until you get it, until you understand, and it'll become second nature. Okay, let's see the next one, unless you have questions. Just going to save it in case I have to go back. The only way you might have gotten confused here is, remember, for the formulas, there are the formulas for proportion and the formulas for count. So you just got to be clear what they want. Here it says the number of people, not the proportion of people, right? So that's how I knew what to do. Okay, this one. I think this one was all right. I gave you one like this before, or we did it in one of the reviews. Okay, this is probability, and you're being asked to use the rules of means and variances. And a homeowner estimates that within the range of likely temperatures, his July electricity bill, Y, in dollars, will be 90 plus 5T, where T is the average temperature for the month in degrees Fahrenheit. So there's a fixed cost plus the effect of the temperature. Right, this is the fixed portion, the 90. If the average light temperature can be represented by a random variable with a mean of 24 and a standard deviation of 4, find the new mean, in other words, and the new standard deviation for the July electricity bill. So for this, you would use the E operator. So the mean, actually let me write it as the mean for Y. Now you don't have to be so fancy. I know what you mean if you just write E of Y, and then I'm just reading comment. Okay, Jen, I'll have to look at what you wrote and see if I can give you some credit I'm not sure why you're confused. Did you divide? Did you do something to proportion the parents and the kids? Let me see. Sometimes the questions, if you have questions, always just ask me if it matters, just text me or email me. I'm available. I'm not going anywhere. Let me see what it said. If the chance of catching the flu at a daycare center is 20% out of 400 children. Oh, out of 400, what is that? The people catch the flu. Oh, so yeah, I said children, and then I said people. Yeah, maybe that's confusing. I could have said children and children or people and people. So I'll see what you did, okay? Back to this problem. Okay, E of y is the same as E of 90 plus 5t. And the mean of a linear combination, or this is called the linear transformation, is the same as a linear transformation of the mean. Okay, Jen, that's good. About 10% is the answer. All right. So this just works out that it's 90 plus e of 5t. And we know the mean of the transformation is just 5 times the mean of t. So plug in what we know for the mean of t. Temperature has a mean of 24. And we're done. You see, when I first introduced this, I'm sure it was much more confusing than it is now. That's how it always will feel with statistics, because you do have an intuition. I just have to hone in on that intuition, or help you hone in on it. Okay, so then 5 times 24 plus 90 is 210, and that's in dollars. Is that correct? Okay, let's do the standard deviation now. The rule for standard deviation, I'm going to take the short form rather than the variance, and we said that the standard deviation of a linear transformation is going to be, if it's a plus bx, it's going to be just b sigma x. So I'm going to use that rule. And let me go back. So this is 4 is the standard deviation. Okay, so for us it's the sigma y is equal to all we care about is the 5 in front times sigma x. So 5 times 4, or $20. Okay? So the b was, just to be clear, it was 90 plus 5x was y. So this was a plus bx. The b was 5. We just take the scalar in front, the multiple in front. I also taught you the method, if you use the variance, you just have to remember to take the square root after. This is much more short. If you can use this for the standard deviation, it's much more efficient. All right, but it derives from the rule for variances. And that's it. Now I'm at the third one. How did you guys do on this one? I actually pulled this out off the internet, and I did not solve it. So if you want to see me solve this, let's see. In Joe's Cafe, 70% of customers buy a cup of tea. So this is the bin, right? And the other problem was probability. Okay, so for bin, 70% of customers buy a cup of tea. So we know this is the proportion of people who buy a cup of tea. This is our P for like the true P. Okay, so we're getting to see now, in a random sample of 20, so that's my n, customers find the probability that more customers find the probability, there should be a comma there, that more than 15 buy a cup of tea. So if you want the exact one, you would have to, okay, so this is a binomial problem. Let's write out the answers below. So A, X, N, P, K. So if you can answer, you can find all those, identify them, then you have a binomial problem. So N is 20, and X would be no cups are sold. 1, 2, ... Let's use this one. And then we're going to more than 15. 15, 16, 17, 18, 19. Oh, I ran out of space. Hope I don't regret this. That won't let me just take that. Okay, 18, 19, 20. So all of these, starting at 16, I have to calculate the probability for each of those, right? Because it says that more than 15 buy a cup of tea. So P is the given 70%. And K is what I'm interested in, right? 16, 17, 18, 19, and 20. So you have to calculate the probability for each of those. You could also go online and find a table. Maybe you find a binomial table that would help you, provide you with those parameters. You have the whole distribution, and you can just pluck out these items and add them together. Or you could use Excel. Or you could use a normal approximation. Can you use it here? Let's just do a quick check. See, n times p. N times p is 20 times 0.7. So that's going to be 14, right? So that's greater than 10. But what about n times 1 minus p? I think that's not going to work. So 20 times 0.3 is not going to work, right? It'll be 6, so it's not greater than 10. So we have to do this one by one. Okay, we have to do them one by one and add them together. I'm not going to do it right now. So you practice that. If you didn't get the answer, plug them each in and add them up. So that's how you would do that one. So try that if you didn't get a chance or you didn't do it properly. The next one, the proportion of customers who buy a chocolate muffin at Joe's Cafe is 35%. So this is a new probability. Find the probability that Joe sells the first chocolate muffin to his 5th customer. Okay, so you have to translate that problem into the techniques that we've learned. So let's do the second problem. Let me erase what I've just done so it can still, I don't have to scroll down too much. I'm going to erase what I did. Okay, what do we have? We have, for B, no, that's not what I want to do. There we go. Okay, for B, ignore the 3 dots there. For B, The proportion of customers that buy a chocolate muffin is, so we're going to do again X N P K, right? X N P K. So we have now a P of 35%. There's still 20 customers we're talking about. Let me go back up. Sorry, okay, first chocolate muffin to his 5th customer. So that would mean that do I still work with the 20 out of a sample? Let's stick with the 20 because there's still 20 in the next one. Okay, so I think this is, let's see. So X is going to be equal to 0, 1, 2, 3. I'm skipping this. Let's see. I'm going to put 3, ignore those. 3, 4, 5, 6. I have a feeling the first chocolate muffin to his 5th customer. So it means that he didn't sell to 4 of them. No, this is different. This is not a binomial problem. Oh, I'm gonna have to see what you guys did. See, it's always a problem when I pull questions I haven't attempted. I shouldn't do that. I rarely do it. But I wanted to give something challenging. Okay, so just making sure the first one was binomial. The second one is not binomial. I'll see what you guys did. Let's it's not binomial because I don't understand the question. I mean, I cannot frame the question in terms of the binomial setting, number of successes out of 20 tries. This is about the order. This is more of a Poisson or something. And it's not binomial. So I am not going to do that one. And if you did it, I'll give you credit. So it's really important, oops, go back. It's really important to know what's binomial and what isn't. Oh, what happened? Okay, so let's see. C, assuming that buying a chocolate muffin and buying a cup of tea are independent, that means if someone buys a muffin, then it doesn't affect the probability of buying tea. Tea is still bought or purchased with a chance of 35%. Find the probability that in a random sample of 20 customers, more than 15 buy a cup of tea and at least 6 buy a chocolate muffin. Okay. So if the event of buying a muffin and the event of buying tea are independent, then buying them repeatedly, so the combination of them is also independent from another combination. So in this case, find the probability that a random sample of 20 customers buy more than 15 buy a cup of tea. So there's 15 cups of tea. So what we got to do is find the probability of 15 so let's call X number cups of tea out of out of 20, and we'll call Y the chocolate muffin. So I want to know X greater than 15, and for Y is the number of muffins, we're assuming people are buying one, out of 20. So the number of people who buy a muffin out of 20. So the probability of Y at least 6. So 6 or more. And then I need to calculate those two and then multiply those together. Okay, because I'm looking at the variable which is binomial, and the sum of independent events is independent, and the sum of these independent events for Y are independent as well. So if I take the probability of the sum of them, which I'm going to have to add a bunch of probabilities together here and then also here, I can just multiply them. So once I get those, I can multiply them. That's my answer. Okay, I'm not going to work it out, but that's how you would solve it. So it was, I gave you extra time to do that because I knew it would take long. I'm sorry about B. Hope it didn't waste your time, but I'll see if I have to give people credit for that. And that's how you would do that. Okay, so the key here was knowing that you would have to calculate this, and this set of events would be independent from this set of events. So you can just multiply these together. Questions? So find efficient ways to do these for long problems. You know, make an Excel table for yourself. Learn how to use Excel for that. Ask me if you need to learn how to use Excel from me if you can't figure it out on your own, so I can help you with that. Okay, so since you're at home, I'm going to give you something a little more challenging, but you have to be more efficient by preparing for problems like that. Find yourself find yourself a binomial set of binomial tables online, or just figure out how to set it up in Excel to make your life easier. Okay? And if you don't know what I'm talking about, ask me and I'll spell it out more clearly. What I'm going to do is I'm going to pick up where I left off. We completed the introduction to the formulas the formula for inference on a population proportion. Okay, so this is the formula sheet that I asked you to have close at hand. So we talked about the confidence interval formula, the sample size estimation formula, and this is for tests of hypothesis. This is where I left off, and what we conducted was what we call a left-sided test, or a left-hand test. So we should do some other tests so you know how to do different ones. So 3 different kinds of tests, right? There's the left, there's the right, and then there's the 2 sides. So what am I talking about? So this is a huge set of notes, right? Because I have a number of problems and answers. So you see here's the set of answers for the problem we did yesterday. And it's nice and neat compared with my written work. I hope that your notes aren't garbled like this. Let me know. I'll send you a clean set. I apologize. So all the notation on this have been bumped over to the corner. So this is the next problem we're going to do. So it's funny as I have all these vaccine problems I created. So that's nice and timely. So let's see. Another vaccine problem. Okay, how do we set this up? One measure that is of critical importance for the practice of modern medicine is the proportion of patients that experience an adverse reaction to a vaccination. Some clinics examine every record to determine that proportion. In a large practice, though, taking a census of the records can be time-consuming. Suppose instead a random sample of 2,500 patients is obtained from a large clinic. So I use the keywords, right? So we can use our formulas, large clinic. Also assume that as a result of past census studies, it is known that the proportion of patients who have an adverse reaction is 1%. Okay, so this is the information. We have an N sample size, and we have this. This is previous study results, right? Previous studies. So for this problem, I'm going to set up, we're going to do problems for the sample proportion. So we're going to need the true mean. If we don't have it, we use sample results to make an estimate. So here is, this is past census studies. This is a past census, so this is actually not a sample. It's a sample, but it's a complete sample. It's a population, actually. So this is going to be from the census. So this is going to be assumed to be your true P, population proportion. Okay, 1%. What is the approximate shape of the sampling distribution of the sample proportion? All right, so what is this? I'm asking you, so as whenever you do these problems, you have your formula sheet next to you. This corresponds to formula number 2. Since we have a large population, a large clinic, right? So we're assuming that means that 2,500 times 10, so that's 25,000. It's larger than, the clinic is larger than 25,000, right? 10 times the sample size. So we're going to use large to mean it's large enough for us to apply our formula. So the shape then, in approximation, the sampling proportion p hat is approximately normal. I'm not going to say the mean and standard deviation because I have that in the next part, but it's approximately normal, right? Since n times p, 2500 times 0.01 is 25, and that's greater than 10. And n times 1 minus p is even bigger, right? Because it's going to be 2500 times 0.99. And this is also going to be greater than 10. So with the clinic being large enough and this being satisfied, the sample proportion is approximately normally distributed. What's the mean and standard deviation? We know from formula number 2 that the mean is, I can use my symbols, the mean is p, and the standard deviation is p times 1 minus p over n square root. So you have to calculate those. Okay, so I'm just using the results from SDS. So that means this is going to be 1. Very small, and then the standard deviation is going to be 0.1 times 0.99 divided by 2500 with a square root. And all these answers are in the notes, but I'm spelling it out for you if that helps. Times 0.99 divided by 2500 square root. So just giving myself some space. 0.0020. I'll have to round it. Otherwise you keep 4 decimal places. Right? So the mean, I'm running out of space. The mean is 0.01 and the standard deviation is 0.0020. So now I'm ready for the questions because I have my distribution and I can answer questions about outcomes, possible outcomes. What's the probability that more than 2% of the patients in the sample will experience an adverse reaction? The probability in the sample, right? The sample proportion, that always goes when we're doing the SDS problems, we're using the statistic as the variable. More than 2%. So what do? I go back to my distribution up here and I use the mean and the standard deviation to standardize. Converting this into the number of standard deviations from the mean becomes a z. So 0.02 minus 0.01 divided by 0.0020. And I hope you can see that. Oh, I want to get rid of that. Let me just this is 0.1. So when you punch that in, 0.02 minus 0.01 divided by 0.002. So you get P of Z greater than 2.24. Now I'm only rounding to 2 decimal places, right? Because I have to use my table, the Z table. So let me check if I did this right. Let me go forward to the answers. Is that what I got? Did I do something wrong? I think I noticed the number seemed weird. 0, 1. Oh, I did something wrong. Yeah, why did I do that? The square root thing. You guys didn't stop me. Okay, because I'm on a delay. There's no square root there. I already did my square root above. I always do it above so that I don't do it twice. So I need to fix this. Won't let me go back. Take off that square root. No. There's no square root here. Just standardize. So if you standardize, can't get rid of that in any easy way. Well, let me try with the canceling. Let's see. No. The value of edited videos. Okay, now I gotta try and get rid of this. Okay, let's do one more time. The notes are there, but just let's correct this. This is P, this will be a Z greater than 0.02 minus 0.01 divided by standardizing by 0.0020, and I got carried away doing a square root. I almost did it again. So this will be P of Z greater than 5, and we know that that's so small it's close to 0, right? Because 5 is off our charts. It's over here, and we say there's not anything really over there. We just say it's 0. Okay, so the chance that more than 2% of patients in the sample will experience an adverse reaction is 0. In fact, there's always a risk. Any kind of medical procedure, there's a risk, but it's very small in this example. Well, at least for 2%. I didn't do for the 1%, but that's what you find out. Okay. Next problem. Now, we've done a problem with SDS. Let's do next a hypothesis test. So do we have 10 minutes to go? Let me see. Do you have any questions? Because maybe I'll hold this for tomorrow. I mean, not tomorrow. For Monday. Well, let me set this up. I think it's important to set this up before the weekend so you have some more examples if you're still confused about, well, I've only done one example, but if you still need help with hypothesis testing. Proponents of vaccines believe that the likelihood of an adverse reaction is very small. They actually believe it is 0.1%. They also insist that they have evidence to support their belief. If from a large clinic, 100 people out of 2,500 were found to have had an adverse reaction, is there evidence against the claim of public health officials? So, what you have to unravel here is what is the status quo and what is the test. Remember our steps, our HAPC steps. So first, hypothesis. What is the status quo statement? Okay, I have trouble with my dots. Let's do this again. I will write this up and put the dots later. Remembering for every single problem, whatever number I put in here as the statement of status quo, I have to put the same number here, and this always is equal. But I get to decide if it's less than, greater than, or not equals for the alternative. Okay, so I actually grade this part of your quizzes or tests that you actually properly set up the hypothesis, because if you set it up wrong, I have to penalize you somehow, and I don't want to just give you 0 for the whole problem, so I'll give you a penalty here and then grade it with the mistake you've made. Although I shouldn't even do that, because really sometimes it makes it really easy. So don't get the hypothesis wrong. I'll be very strict about grading the rest of it, okay? So the status quo. What is the status quo? What is the current belief? What is the belief in this case of the public health officials? That the proportion is actually 0.001 is their belief. So that number goes here. 0.001, and it also goes here, 0.001. And what we're going to do is test if there's evidence, significant evidence against that. So is there evidence against the claim? Okay, so we have to decide, is this a problem? Are we looking for it to be less, to be greater, or not equals? I could work with this, that they actually believe it's 1%, 0.1%. So then it would be, this would be a greater sign. But if I'm not clear, you should use the not equals. I'm going to see what I did here to be sure. I use not equals. So I wanted this to be an example of not equals, but if you went ahead and said, well, the others, the alternative is to think it's higher, you could put a greater than sign. But what I'm going to do is do the test for not equals when it's not exactly clear, so I can show you the other kind of test, okay? Because there's the less than, the greater than, that is the left-hand side test, and then the right-hand side test is greater, and not equals is a two-sided test. So we're going to conduct the two-sided test, and this is the alternative, what we believe to be true if we have evidence, significant evidence against the null hypothesis. Sufficient evidence that makes the test significant. All right, so that's the first step. And I have no room. So let's see, I'm gonna trying to figure out where I'm going to find room. Okay, let's put another sheet in. So the next step is assume. Assume what? Assume H naught is true. Then the P must be equal to the hypothesized P, which was 0.001. So we're going to assume it's true. As a result, then the sample proportion will be approximately normally distributed with a mean of P, 0.001, and a standard deviation of P times, I'll do it below p times 1 minus p over n square root. So this is my new standard deviation. This is the standard deviation for this exercise. And I'm only able to do this because I assumed I know p, okay? So this is using formula number 2 as though I know p, even though we don't know it for sure. We are suspicious, but we assume it to be true. So we put in 0.01 times 0.999 divided by, I think it was 2,500 in the sample, and that's my square root. And that will give me, just going to double check that that's, yes. So punching that in, you get 0.0006, 4 decimal places. You should be doing this with me. I'm giving you enough time. Okay, so this is 0.0006, very small. All right. So what do you do with that? That's the assumed step. We're going to use this distribution to assess the evidence in the next step. But it's 6 o'clock. I'm going to refer you to the notes to proceed, and please, I'll continue on Monday. If you have any particular questions, please send them ahead. But otherwise, have a good weekend. And I will just continue with this. We have still another 2 weeks before we complete the material. So that's a lot of time to get through what remains. So just keep up with watching the videos, keep up with reviewing the notes, and you're going to be just fine. And I will post your grades as soon as possible. Okay, good night.